All right, so what we're going to do today is we already know how to graph some shapes and find the area of that shape. If we know the equations, we know how to do that. So that's what we learned how to do Thursday, Friday. Okay, what we're going to do now is we're going to make a 3D solid, and we're going to be able to find the volume. Okay, this is how we're going to do it. We're still going to start with the base, which is what we did before. So the area that we did before, you kind of think of it like area of the base. And we are going to stack 2D shapes perpendicular to the base. So they're going to be coming out from the paper, kind of like on the z-axis. The z-axis is like the one that comes, it's like depth, okay? This is very difficult to visualize because every problem is going to make a different picture. But if you know 7.1 really well and you remember these formulas, this really isn't that hard to do. Even if you can't visualize a problem, you're going to be able to solve it. Okay, so remember how in the old problems you had to decide whether you were doing a problem with respect to x or y? And really, you could have done any problem either way. That's no longer going to be an option, which isn't a bad thing, by the way. So I'm going to skip all the way down to here. See how this says perpendicular to the y-axis? Think about what that means. That means a horizontal rectangle, which means with respect to y. So you're going to look for this word, perpendicular to what axis? That's going to tell you whether you're with respect to x or with respect to y. Okay? Before I get too into this, I want to go ahead and review these, and then we'll get into like what this actually means. Okay, if a square has a side s, what will its area be? S squared. Okay, does any of you remember the equilateral triangle formula? It's not 1/2 base times height. It's an equilateral triangle, and every side is s. So it's like a number s squared. 3 is in it. It's 3/4 is pretty close. It's square root of 3 over 4, s squared. Okay, and there's a reason I'm using this instead of 1/2 base times height. See how that has s squared and now this has s squared? It's going to make these two problems really similar so that if you can do a square, equilateral triangle is super easy. If we tried to use the 1/2 base times height formula, it would be harder. Okay, so this is a good thing. Okay, what about a rectangle of base s and height h? S times h. So rectangles are always going to be a little bit different because they have a different height. The height could be a number, or it could be twice the base, or something like that. Okay, semicircle. Okay, what does semicircle mean?
Half of a circle.
Half of a circle. Okay, I'm going to write this down here. I'm going to write half pi r squared. Except they don't say with radius r, it says with diameter s. And there's a reason I'm picking s, by the way. I'll explain why it's s. But if the diameter of a circle is s, then what's the radius? Half of it, yeah. Okay, so this is kind of strange, so let's clean it up. A half times pi times a half squared.
1/4 pi s. Oh,
Close.
No.
What's a half squared?
So it'd be an eighth.
A quarter, and then times another half would be an 8.
An eighth pi.
So pi, we could say an 1/8 pi or pi over 8 s squared. So again, I really just want to emphasize there's an s squared, there's an s squared, here's an s squared. What this is going to allow us to do is not every problem is going to be like a brand new problem. Okay? They're related. And there are more than this, but these are the ones that we're going to see in this class, okay? All right, so we're going to put a pin in this. We're going to come back to it. All right, that was just kind of review, although I didn't think you had seen the pi over 8 before. Okay, you see these pictures? Are they a little intimidating?
Yeah.
Maybe? No? It kind of, that's probably a preference thing. Okay, what I want to show you, and by the way, if you go to the timeline and you go for today, you're going to see 3 links. The top link looks like this, and it looks like the one on our paper. Okay, I just put that on there for you. Okay, this middle link is what we're going to spend most of the time on. The third link we're not even going to get to. So we're about to do the algebra or the calculus of this problem, but I want you to think about this. You have a circle, okay, and you see, we've seen this before, an approximating rectangle, okay, but instead of it just being, and you can open this up on your computer, by the way, all right, I have the links right there on my timeline for you to do it. So if you look at this, if I could figure out what that distance is, what would I need to do with this distance to find the area of the square? Square it. That's what we said, s squared. So s is going to be the distance from one side of the graph to the other side. This may be top minus bottom, it may be right minus left, okay? That's how you're going to find the area of one square. Then what we're going to do is we're going to watch what's happening here. As I add squares, keep doing a square. Every time we have the area of that square. How would I find the area of the whole volume if I put in all the squares? Like if you knew the area of each square, how could you find the volume of this shape?
Multiply each area by
Did you do something with the integral?
Yeah, but just in general, what do you thinking you need to do to all the areas to get the volume? You have to add them, and that is what an integral does. It accumulates, it adds up all the things. So we're going to integrate. Let me kind of go back one more time to show you. We're going to integrate from one side all the way to the other, the square. The area of the square. It's what in that calculus is going to take the area of the squares and it's going to add them all up. This is like Riemann sums on steroids. Okay, this is like a 3D crazy Riemann sum because we're not just talking about rectangles anymore. We're talking about a base that's some shape, and then these figures that are popping out of it. Sometimes they're going to be squares. Sometimes they're going to be semicircles. I mean, there's such a wide variety of what you could do. All right, so we got to have some kind of overall rules here. Okay, so I want you to go down here, and this is just there so you can kind of see, remind you of what we did. All right, and so what I would like to do is just work with something we already know how to do, which is area. Okay, and I want to show you how if you know area really well, then you know how to do volume. Okay, it's just an extension of volume. So see how this says solve for x? Let's do that. Then x squared would be the, sorry, I'm getting ahead of myself here. All right, x squared would equal 25 minus y squared. And then just x is not 5 minus y. That's math gel if you do that. Okay, it is going to be the square root of 25 minus y squared, which does not simplify to 5 minus y. Okay, and then I'm going to put a little plus minus here. Okay, what this represents on this graph is, okay, this semicircle right here is the equation x equals square root of 25 minus y squared. Okay, I'm going to do this one in a different color. This part of the circle, since it's the left part, would be x equals negative square root of 25 minus y squared. Okay, so the right side is one piece, the left side is another piece. It's not, by the way, this is not always going to be a circle from now on. This could be any of the shapes that we've already done. I'm starting with the circle because it's kind of the easiest one to visualize. Okay, so we got this as x equals in terms of y. And do you see how this says perpendicular to the y-axis? All of this is telling me, hey, do the problem with respect to y, or in terms of y. So back to just area, okay? This is what we did Thursday and Friday. We would go bottom to top, right? Integrate -5 to 5. And then what we would be doing, sorry, I'm going to write this in a different color. The area would be integral of -5 to 5, okay, bottom to top. And then we would just, remember how we draw those approximating rectangles? And you guys are like, why do we need to do that? Well, it's going to make a little bit more sense with today. The way we found area was we just calculated, well, how long is that? It's right minus left. So square root of 25 minus y squared minus negative square root of 25 minus y squared, dy. Okay, that's just finding area. To change this into a volume problem, we're only going to have to do something else. Just one more thing to it. Okay, let's go ahead and plug this in to the calculator. So we'd go F3, integrate, and then we would do the square root. I'm just going to type it all in. And then remember at the end, comma y, comma -5, comma 5. This is something you should know how to do for the quiz tomorrow. Typically, though, these equations are different, you know. In a circle, though, the two semicircles look similar. Those of you that don't have a calculator, I want you just to think logically, what's the area of this circle? I got 25 pi. Logically, does that make sense that the area of a circle with radius 5 would be 25 pi? Okay, that's old. Okay, so how do we take this information and put it into the problem like this? Okay, well, instead of just having a line at the bottom, we are going to have a square. But they're related because, see, basically what's happening is you have a square, and it's very hard to draw, but this square, imagine it coming out at the paper at you, okay? That square has a side of S, which we already said was this. Let me circle this. This piece right here is the same as S. We're just giving it a name now. We're calling it S. Does that make sense? So what would the area of the square be? It would be S squared. So the volume is going to be the exact same problem, okay? We're still going to integrate from -5 to 5. That's still bottom to top. Except that I'm going to take this whole thing, which is S, and I'm going to square it so that it actually finds the area of this protruding square, and then the integral will add them all up. So if you know how to do the area problem, you can do the volume problem. It's really not much different. See, I'm just taking that body of that integral and I'm squaring it. I can't square my answer. I got to square the body of the integral. Do you all understand why I'm squaring it? Because that's the equation of a square. You go S squared, side squared.
So if it were a different
Like in other words,
you would use.
yeah, we'll get to a different shape here. But in other words, this is S and this is S. So the area of that square is S squared. Well, what is the distance between side to side? It's right curve minus left curve in general. Or it's top curve minus bottom curve if we're doing this with respect to X. Because these are changing. Like if I drew this rectangle somewhere else, it would be different length. They're really big in the middle of the picture and really small towards the edges. That's why we can't just say a number squared. It has to be an expression squared. Okay, and the expression is going to be right minus left.
Always, or just for
Well, if you're with respect to y, yes. If we were with respect to x, what would we do?
one?
Top curve minus bottom curve. And that is really the hardest part to get straight. Once you get that straight, a lot of things fall into place. Okay, so in your calculator, you don't need to retype this whole thing, by the way. Sorry if you've already done that. Here's what I'm going to do. I'm going to stop just short right here, this comma y. If I want to square that whole thing, I'm going to start at the end. I find this to be the easiest way to do this. I'm going to put an extra parenthesis, squared, and then I'm going to go to the front, and right after the integration symbol, I'm going to put in an extra open. And when I press enter, I should make sure that this whole thing is being squared. A common mistake would be just to let the second piece be squared. So the good thing is we do not have to integrate this stuff by hand. The bad thing is you can mess up with your calculator, so you got to be careful with that. All right. Say that again.
So when you found the area the first time,
Right.
you can't square that, right? Because
Correct.
you're not squaring. That's like squaring the whole thing.
You're not squaring the integral. You're taking the integral of the square.
Yeah. Okay.
Because remember, we're adding up squares. And add up and integrating, those need to kind of go together a little bit. The integration is what adds up all those areas. Okay, we did a lot of work for that. So we kind of earned ourselves a little break.
Yeah.
So here's the deal. If you've already done a square problem, and then I ask you for a semicircle problem, remember how semicircles were related to squares. You just had to multiply by pi over 8. Pi over 8, that's a number, right? In an integral, can't we pull the number out to the front? So I'm just going to do pi over 8 times 2,000 thirds. And you don't even have to simplify. Of course, you could simplify if you wanted to, but you don't have to. Do y'all understand how I did that? I do want to go ahead and show you what the semicircles would look like, so that you understand why it's different. Okay, in this thing, and you can kind of go in here and do this if you want. Why didn't I want to change the semicircle? There we go. Okay, so same base. And the base is not always going to be a circle. It's just, this is the problem we're starting with. And we have a semicircle. Do you see how the diameter of that semicircle is from edge to edge? It would be top minus bottom or left minus right, depending on which type of problem you're doing. Okay, that's one semicircle. Pi over 8 times s squared. If I integrate it, it would add in all the semicircles. And this is going to make a shape that you should recognize. What shape is this? It's a dome, or it's like half a sphere, a semisphere or hemisphere. Okay, which there is a formula for, by the way, but it doesn't even matter if we know it. Okay, equilateral triangles. If you've already done the work of the squares, you don't have to start over with an equilateral triangle. What was the multiplier on an equilateral triangle? Square root of 3 over 4. So square root of 3 over 4 times 2,000 over 3. And I can do this because square root of 3 over 4 is just a number. Just a number. Okay, here's what I would like for you to do on D is scratch out the y. We're just going to say a height of 2, not 2y. Okay. Rectangles are different. In a rectangle, there's no s squared, right? We are going to have to restart this one. But it's not like total, it's still related. You're still going to go integration bottom to top. But what's the area of a rectangle with a height of 2 and a base of s?
2x.
2s. So we just go 2 times this thing. Square root of 25. Like, no matter what shape you're doing, s is going to be the same. And s, a lot of teachers say it stands for slice or side. So in my calculator, I got to get rid of the squared, or I could just go back up here and I could put, well, I mean, there's a variety of things you could do. Since it's just times 2, you could just say times 2. You could put it in the integral or out of the integral. Either way, you're going to get 55. Rectangles are going to get a little trickier than this because sometimes it is going to say height of 2y, or sometimes it's going to say a height that's twice the base. We'll deal with that as we get to those, okay? Okay, I want you to turn the page because I want you to see the variety of problems. We're going to look at number 3 and then we're going to be done. Okay, so we got to graph this. Looking at those equations, does this look like a with respect to x or y problem? It looks like a with respect to x problem, and it is, because I see this phrase, perpendicular to the x-axis. Okay? So let's go ahead and graph these. The line is pretty easy to graph. Slope of 1. The parabola, not too bad. I'm not going to spend a lot of time on this right now. Given your calculator, you should be able to graph anything. Okay. The shaded part is right in here. So if you were just finding the area, it doesn't ask for it, but let's say I'm just going to put it in. If you were finding the area with respect to x, what would be your limits of integration? Make this bigger. Meaning, what would be the bounds on your integral? 0 to, what's this x value?
1.
It looks like 1.5. We don't know for sure. There's several things we could do, though. We could graph them and find the intersection. We could say, hey, F2 solve. Set the two things equal to each other. X. You need to be proficient about, I mean, you got to figure out how to do these problems. So there's a lot of tools in your toolkit. Make sure that you're able to solve them. Okay, I get x equals 3/2 or x equals 0. You could find the intersection, though. That would work as well.
Wait, so what you did, you said...
I just set them. Intersections are where two curves are equal, right?
You said the curves equal to
I just set them equal to each other. And so that ends up being 3/2, which is 1.5. So that would be 3/2. And we would do the top curve minus the bottom curve, right? A second ago, we did with respect to y, so it was right minus left. Now this is with respect to x, okay? And our s is vertical in this case, so it's top minus bottom. That's how long that little s is. So that would be the line, which is x, minus the bottom, which is 2x squared minus 2x. Okay, that's what we did before. This is what you're going to have your quiz over tomorrow. What's new today is figuring out volume. When you're doing a square, all you have to do is take that s, okay, which used to just be fine on its own, and square it. So it'd be 0 to 3/2, and then I'm going to put that all in parentheses. And I'm going to square it. Okay, so in our calculator, I'm going to integrate. Be careful with this. When you know you're going to have to do integration and square, just go ahead and do integration open, open, because you're going to have to do both of those. Be very careful with your parentheses. Okay, 81 over 80. Okay, remember though, once you do a square, you can do a semicircle, you can do an equilateral triangle. Those are super easy. Semicircle, what was that thing we got to multiply by for a semicircle? Think about a circle. A semicircle is the one with the pi.
Oh, pi over 8.
So pi over 8. So we go pi over 8 times 81 over 80. It's fine to leave it like that. If this was multiple choice or something, then just say, hey, times pi over 8. Like, you got your calculator here. Okay, 81 pi over 640. I should have been able to do that without a calculator. Okay, equilateral triangles. You know where the square root of 3 comes from? It comes from a 30, 60, 90 triangle. So here the volume would be square root of 3 over 4, again, times 81 over 80. And so that's going to be 81 root 3 over 320. And you don't have to do that. You can just leave it, meaning you can just leave it as that one. Okay, rectangles are always different. Rectangles you always have to stop and think about. Okay, how do you find area of a rectangle? You do the height times, in this case, the S, the base. So the volume is going to be the integral from 0 to 3/2 of 3 times S. Which in this case is just going to be like the area, but times 3. So if you want to go up to the last thing that you did, and you want to say, hey, I don't want the square, just go and subtract the square. Don't retype it. And you know you want to multiply that by 3, well, you can just go times 3 right there, or at the end, or at the front, variety of ways, 27/8. Okay, tomorrow I am going to go over this big example. Okay, your homework tonight is this. You need to focus on the area homework. And it looks like a lot of problems. Guess what? It's 1, 2, 3 problems with some parts. But, okay, tomorrow, you don't have to have this done by tomorrow. Okay, tomorrow we do area quiz.